Okay, great. So welcome to day 11. Someone asked why we're wearing these masks in California. There is a law now that we have to wear masks inside because of COVID, version 2 or whatever. So anyway, sorry about that. So today we'll be talking about bicomodules, and basically those generalize everything we've done so far. So we've talked about poly, and poly is basically, we're going to be writing it as though like the entire story takes place when this is y and this is y. Polynomial functors live there. They will be bicomodules from y to y. But we're going to be using bicomodules between two categories, C and D, and that's going to be the generalization. And they generalize. You can add these, you can multiply these. Like the category of these is closed under limits and coproducts. When you just fix C and D, but you can compose them, you can multiply in various ways, you can tensor, and so we'll be doing that. So, so for the people who like abstraction, maybe I need a new marker here. Mike Schulman, in his paper Framed by Categories and Monoidal Fibrations, says that if our tensor product composition preserves equalizers, then, and this is very abstract, so I'll be done with this part in about 40 seconds or 30 seconds, then we can form, I'll just do this on a new line, still in 30 seconds, we can form comod of poly. And the story we're talking about, and this is what's called an equipment, and we'll be getting to equipments not tomorrow, not next time, but the time after that, the last class. So he says we can form this thing, and this is the thing we'll be talking about today. The objects of these are called polynomial comonoids. Those are categories. The vertical morphisms here are cofunctors, and the horizontal morphisms are these bicomodules, and it just works by abstract reasons. And so today we'll be talking about what that means for poly. So yeah, so just a little bit of like, I don't think Nelson or I claim priority or whatever the word is on most of this stuff. We just learned it ourselves, but I can tell you just a few things that I do know and that really like move this story forward. One is the Amon and Ustaloo paper, Ustaloo of 2016, that said comonoids and poly are categories. Now the morphisms are cofunctors, not functors, but still, the objects up to isomorphism are categories up to isomorphism. And then Richard Garner, in his hottest video, said that bicomodules, and again, this is very abstract, you don't have to know these words, are parametric right adjoints. And the point of today is to start talking about this stuff and bring it down to earth. So these are basically the story that tells us all about the framed by category comod poly. And let's start with that. Oh, so today, bicomodule basics. I was calling these bimodules because bicomodule just sounds so long, but it's probably better to call them bicomodules. So today, bicomodule basics. Next time, Nelson will tell us about bicomodules as parametric right adjoint functors. So as functors with a special property called being a parametric right adjoint. It sounds like it's a good kind of right adjoint, but it's actually a bad kind of right adjoint. It's almost a right adjoint. So prof functors are almost right adjoints. So that's what Nelson will talk about. And then the next class, which is like next Thursday, which will most likely be the last class, I'll talk about data migration, which I might get to today, but probably not, and dynamics. So the basic idea of the dynamics is that, I'll just for very basic, When C is Y, the terminal category, the category with one object and one morphism, then a polynomial from C to C is a regular old polynomial. And those are our polynomial functors. Those are our interfaces that we've been doing the whole time. The dynamical systems were maps where it was a set X and a map from X to P composed X. And again, you don't have to know what any of these symbols mean. I'm just talking. And if you happen to watch this afterwards or know these symbols, then they'll make sense. But the dynamical system story was like we had a polynomial interface, we had a set X, and we had this map from XY to the X to P, something like that. And that was dynamical systems. Now what we're going to do on Thursday, next Thursday, is we will see that we can repeat that entire story, except that the positions and directions of P are somehow living in an ontology. It's as though there's a category C, and instead of like when we can actually classify the positions as being, telling us there's a schema for positions and directions. That's kind of how this is going to generalize. So we'll be doing dynamical systems, except where you can kind of classify all of the different positions in your dynamical system. But for today, let's talk about bicomodules. So 2, definition. I'll just write it. So def, so let C and D be comonoids in poly, or categories. A C-D bicomodule consists of a polynomial, regular old polynomial functor, like we've been talking about the whole time, P. 2. So C and D are cat-sharp. They're like a polynomial, an epsilon, and a delta. And D has a polynomial D, an epsilon, and a delta. Okay, so we have a polynomial. We have a map from, well, let's just say we have 2 maps. From P to P composed C, and from P to C composed P, and from P to P composed D. And so what you'll notice is that the P is on the inside. This is just notational, so you can remember what's going on. It's like P to C composed P and P to P composed D, so P is on the inside in both cases. And so I'm going to denote this. Denoted. C, D, P. So I take these little triangle symbols that mean compose, and I put them at the end of the arrows, and I kind of say P to P compose C and P to P compose D. So the P, C compose P and P compose D. So I'm just kind of, that's why I make that notation. Okay, so, but then there's some rules. And these rules, I'm going to write down, them down in commutative diagram form, and then we'll spend a bit of time like unpacking them and making them elementary about elements of these positions and directions and all that. So what does it have to satisfy? Well, first of all, P goes to C composed P, but there's an epsilon for that P, for that C. So we can knock that C out by taking identities. And you don't have to think about it. I'm just writing some abstract things right now. I want this diagram to commute. And I can take P, I can go to C composed P by this, I'll call this guy lambda for left, and this guy rho for right. So I can do lambda, and then I can go from C composed P to C composed P by delta, or I can go this way by C composed lambda again. So I can take the P here and just open it up like that. And I want that to commute. So our job is to write out these laws right now. That's what I want to do. And then I'm going to trace through what some of them mean and then give you all the axioms elementary wise. So we go to P composed D. Now we knock out the D by taking identities, and that should be equal. So there's P composed epsilon. There's rho. Sorry, that rho looks like P. And then there's one more here. So there's going to be 5 altogether. P to P composed D to P composed D composed D. Okay, this one is rho. This one is rho. This one is rho composed D. And this one is P. Sorry, it looks so similar. P composed delta. So I guess you really have to stare at these because of how similar a lot of the letters are. And then there's one more, and that says that if you go from P to C composed D, C composed P, and from that to C composed P composed D, that's the same thing as this. I'd never really worked with bicomodules before, and when I saw this, I thought, like, does that not just follow for some other reason? But it doesn't. This one is C composed rho, and this one is lambda composed D. And that does not just follow for free or anything like that. So there's these 5 laws. But luckily, all of these are laws of the following form. They start with a single polynomial, and they map to a composite. And we have polyboxes that help us do maps from polynomials to composites. And so we can actually just like check what these things say. Right, so let's start writing things out. Let's say here's P, and we're going to go from P to P composed C. Sorry, from P to C composed P. And this will be lambda. And then we'll also go from P to P composed D. And this will be rho. So this is the right one. Oh, actually, before we go into that, sorry, I wanted to note some very simple things. Yeah, okay. Before I go into that, let me go erase this stuff and say a couple simple things here. First of all, these form a category. So a morphism from, if I had 2 different ones, P and Q. The good thing about category theory is you start getting used to what this should mean. What should this mean? Well, I have a map from P to C composed P, and I have a map from P to P composed D. And I have a map from Q to C composed Q. I have a map from Q to Q composed D. And a map from P to Q, if we call it like phi or something, should be a phi there, and then C composed phi. Like keep the C constant and move the other one. This should work, and this should work. Okay, so that's pretty easy. You don't have to check any more laws, just these. And then, so we have C mod D is the category. It should probably be called comod of C, D by comodules. Like this, and morphisms like this. But I want to make one quick note. Note A, if C is Y, then lambda is identity, or if D is Y, and rho is identity. And the reason is because if C was just Y here, then the epsilon is the unique map from Y to Y, and so this would be just the identity. So we're basically saying if this is the identity and this is the identity, then you can always check that the third one has to be the identity. And similarly over here. So if I knew that D was Y and this was the identity, I would know that rho was the identity. And so one more definition, a left C module is a CY bimodule in other words, where D is y, and a right D module. There's another word D module in math, but this has absolutely nothing to do with that. Y D bimodule. And I just noticed I said bimodule instead of bicomodule. That might happen sometimes. Sorry about that. So in other words, if you just wanted to talk about a left or a right module or comodule, you would just basically set the other one to y, and the definition would go through. But all it really would mean is not having to check any of this stuff. Okay, so let's look at these laws. So, or what's happening here? So you start with some position in I, and I just want to call this something. So I maps to some object in C. I'm going to call that object absolute value of I. And then for any morphism in C, so C is a category, it's got objects and morphisms. For any morphism in C, I want to call this thing I.F, just because the notation, there's just so much notation we're going to need that we might as well just like write I.F. It means basically move I forward by F. And then if somebody gave us an x, a direction in x, in P there, then I want to call this thing f.x. So I'm just making up notation right now. So let's say someone gives us an I. What should our row thing do to it? Well, it's going to turn out from this guy that this is forced to be I. And then for any x, for any direction there, let's call this I.x is a position in D. At some point I was writing this I.absolute value of x to make it look like this, but like the notation it's just not worth it in the end. There's just so much notation that it's just probably not worth it. Okay, and then given a morphism here, G, I'm going to write x.g. So note that there's no overlap of notation. Like even though I have I.f and I.x, f is a morphism in C, whereas x is a position in P. And so like no symbol has been overloaded here. And then, so we have these things, and they're supposed to satisfy these 5 equations. And so you can just check what they say, but like, I don't know, maybe we should do one or something. So if I did, if I go to y, so here's epsilon, I'm going to do this one there. Epsilon p there's lambda. This says if I take any I, lambda goes to absolute value of I. This is in C. This is y. I do the scribble to mean there's only one choice here, one choice here. So what comes around when you do epsilon is you get identity here. Identity sub this thing. Then you hit this with lambda and you get I dot identity. You go through P. Oh, sorry. This is P, and this is supposed to be just the identity on P. So you get I dot identity. And then for any x, you get x. This is just identity there. And then you come back around and you get identity dot x. And this whole thing is supposed to be the same thing as just doing identity on P. So, right, this is basically P. Okay, so we start with I, we go to I, we take any x, we come back to x. And so if we read what this says, it says when we start with this and run around until we get there, we get I dot identity is I. And we get that identity dot x is x. So we get these two equations. And each one of these things, you just write it out. You write out these polyboxes things, and you read off what the equations say. And I'll tell you what they all say. They all say very reasonable things when you use this notation. But like what it actually means is kind of harder. So here's all the equations. So I wrote it again. We have this bicomodule between C and D, and it says that there's a map from P to C composed P called lambda, and from P to P composed D called rho. And the laws from those 5 things say these, and these. Okay, so it says that I dot F is cod F. Like if we take where this thing, we take its absolute value, that should be the codomain of F in C of 1. We know that I dot identity is I dot F composed G is I dot F composed G. Identity composed X is X. F composed G dot X is F dot G dot X. So everything is just kind of like moving parentheses around. Over here, I dot X dot G, that's something in this D of 1 thing, is cod G. X dot identity is X. X dot F composed G is X dot F dot G, et cetera, et cetera. You just move parentheses. So from this notation, which is basically meaningless, I just wrote some stuff down, the notation kind of disappears in a certain sense, and like composition and dots turn into each other and stuff. But what's amazing is like what I erased here, which is that Richard Garner showed us that these equations somehow have to do with functors from D set to C set. And that's our goal to talk about. Well, we'll talk about that a little bit today, and then Nelson will talk about it more next time. So, okay. Any questions so far? Okay. So I'm going to erase this part because it's on the board over there. So you follow these things through, and they tell you some elementary equations in the sense that it's about elements, positions, and directions. But what do they mean? So what I want to talk about next is like the case where D is 0. So 3. Oh, you know what I could do is say, what if C was 0? So really quickly, if C equals 0, then P equals 0. And the reason is because if I need a map from P to C composed P, well, 0 composed P is 0. And to get a map from a polynomial to 0 is impossible unless P is 0. So there's only one CD bimodule when C is 0. If that's 0, you're done. P is automatically 0. But what if D is 0? That is not trivial. When D is 0, we're looking at this case. And what we get is something almost was pretty interesting. So first, S must be constant. It must be a set, like 53,000 or whatever. So why? Because we have this map S. S is the name of a polynomial. I guess I should call it P really quick, but in a second we'll see that P, it has got to be P equals S for S a set. Because we have this thing, P to P composed 0. P composed 0 means P of 0. You plug in 0 for P. Every time you see a y in this thing, you throw it away. So it's like if it was like y cubed plus 3y plus 5, y to the 0, then when you, like anything that's not a constant term, when you plug in that 0, you're going to get 0 plus 0 plus 5. So it's just going to, right? So this thing is just P of 0. And now I need that when I include it back into P. When I include the 0 terms into the constant terms into all of it, this thing needs to be identity. So somehow every position is being mapped to one of the constant positions, but then when you map it back and just include it back in, you get identity. That forces P to equal P of 0. And so P is constant. So now we know that the only C0 bimodules, when you look at the carrier, it is a set. And what we get is we get a map from S to C composed S, satisfying some laws, and this is exactly, etc. So a C comodule, a C0 bimodule is what we called a C coalgebra. It's a set S, a map from S to C composed S, and then like these diagrams commuting. If a triangle turns into a circle, it's not a problem because it just means compose. So if you're writing fast and it turns into a circle, don't worry about it. Okay, so these commute. That's what we called a coalgebra. And we said C coalgebras, we said this, we proved it. At least I think we did. We at least explained it. We said that C coalgebras are functors, or can be identified with functors from C to set. So C0 bimodules are functors from C to set, or they're equivalent. And so let me write out this, an equivalence of categories, or like a big equivalence thing. Okay, so the following, so here's the little theorem. The following are equivalent. So I'll just say TFAE next time. Okay, one, like C mod 0, C0 bimodules. Two, functors C to set. Three, discrete op fibrations. So I'm not saying much yet. I mean, not saying, I already kind of said it. Discrete op fibrations over C. A discrete op fibration over C, remember, was a regular old functor from C to D, from D to C, where, like, for all I, di to ci was an iso. You look at the maps out of I, you look at the maps out of wherever it goes, and those should be the same. So we have discrete op fibrations over C. And the last thing that's pretty basic, like all these are going to start, maybe they all seem the same to you, maybe they don't. Cofunctors into C. So discrete op fibrations are like special maps from D to C. And these are special functors, these are special cofunctors, but discrete op fibrations over C are exactly the same thing as Cartesian cofunctors over C. Like if this is an iso, then I don't care if we go forward and think of it as a functor or go backwards and think of it as a cofunctor. It's an iso. So these four are kind of not so, I mean, they all follow from this fact. And the fact that when P is a C0 bimodule, it forces the thing to be constant. But this is kind of weird. So the next one is that these are the same as linear left C modules. So if you have C and your carrier was like AY was a constant polynomial, then that thing will have to be, again, just a functor from C to C. The category of these is exactly, or is equivalent to the category of functors from C to set. And one thing I like about number 5 and number 6 is that there's some alliteration so you can remember it. So linear left C modules and representable right C modules. So if you have, remember, a right C module is something as a Y bimodule. If it happened to be of the form y to the a for some set A, so if A is just a set here, then this must be, the category of these is equivalent to this one, although I need to up it. These are backwards, but the objects are the same, and they're just mapped the opposite way. And then 7, cofunctors from sy to the s to c. But these are all equivalent categories. I had to opt this one to make it an equivalent category, but like it's equivalent basically, except for the op. This one has basically the wrong morphisms. So I guess if I include this one, I can't say the categories are equivalent, just the objects. If I include this one, I have to use what David Jasmyers calls charts instead of like ordinary maps. So this one, number 7, is kind of in parentheses, I guess. But these are all equivalent as categories. Okay. Any questions from anyone? So I want to go through just a couple of these to see. We did like 1 and 2 last time, or some previous time. I don't know if it's worth maybe saying. S is a set. What set is it? It's the category, like if I have a functor from C to set, it has a so-called category of elements. If you take the number of elements in there, that's S. And basically what's going to happen is you take any element of S. Let me go over here. You take any element of S. This absolute value of it is where it goes under the, like, yeah, is where it goes in C. And this, for any F, I dot F is how the category C operates on it. So every element goes to some type in C, and every morphism out of that type operates on the element to give you a new element. So it's kind of like you have C, and you have S, and C is a whole category, whatever, and S is like some gigantic blob of data. But every object in S, every element of S, goes down to absolute value of it, some object in C. And if you map out of that, it gives you a map out of that thing, which we called, well, S dot F. So that's how the 1 and 2 story are equivalent. But like, if we look at, say, linear left, that's like you have this C. If P was linear, it's AY, then that means there's nothing going on there at the top. It's AY to the 1. And so we take any element of A, we send it to C, and it goes to like something. And then for any F, we get A dot F. And so it says for any object in this big thing, we can take its absolute value, and then if you hit it with an F, it operates on it. And that thing is functorial by these two conditions here, if you can read those. And similarly for representable rights, let's suppose you had some P, and P happened to be A to the Y, or sorry, Y to the A. In other words, it has no it only has one position. So there's Y to the A again. And there's D. And there's no data there. There's a bit of data there, and there's some data there. So if someone picks an A for us, then we give it like no data dot A. That's a point in D. And then for any G there, we get like A dot G. So it kind of names a point in D. And then for any map out of that point, it gives us a new point. And that thing is functorial by this condition here. So it's again a functor. And so that's kind of, what I'm trying to say is that this might look imposing, like, wow, how do you figure all that out? And the answer is, you just run this. At some point I called it an abacus, because it's just like this little machine. You run it, you see what it says, and when you're all done, it just tells you something, and that's the answer. So you just run it and see what happens. If you ever like want to prove these things for yourself, it's pretty doable. Okay. So part 4. What about C mod y and y mod C. The word mod sounds like number theory, but of course this has nothing to do with that. So what is the category of, or what are modules from C to Y like, or like this, and what are modules like this like? Okay. All right, so, well, let us tell you some facts about these. So here's a little theorem. The following are equivalent. 1, CY bimodules. So a CY bimodule is pretty surprisingly, so this is a left C module. I guess I should have said left C comodule. What are those? Those are functors from C to poly. That's pretty surprising. Nelson figured that out long ago. That's pretty interesting to me. What else? They are functors, they're cofunctors from PP. So this thing that Josh, so one thing I'm saying by telling you some names is that maybe, I don't think anyone knew this before, Nelson told me, and I'm almost sure no one knew this, but the other day Josh came up with this, this co-closure to composition, if you remember. It was like polymaps from P to Q composed R is the same thing as polymaps from what we denote RP to Q. And here we have this map from P to P to C composed P. So we can do exactly this trick and pull it over and get the PP thing. And it turns out that the conditions on this thing, the conditions that made all these true, force this to be a cofunctor. So cofunctors from this thing. This, if you remember what kind of category that is, I talked about it briefly, it's the full internal subcategory of set. It's like each position of I, each position of P has some number of directions, and this comonoid is just like a full subcategory of set, op, spanned by those sets. So it's kind of a weird, interesting fact. Okay, and then finally 4, connected limit preserving. A functor preserves connected limits if it preserves basically pullbacks and equalizers in any shape that doesn't, maybe I shouldn't say much more. Connected limit preserving functors set to C set. So these are like, that's what it is. Okay, so these are also called profunctors, parametric right adjoint functors. That in our setting, from set to C set, the profunctors are exactly the connected limit preserving functors. Okay, so maybe I can explain some of this. So if you have some P mapping to C composed P, my math keeps falling down. What is that? So let's look over here, I guess. Every element of P goes to some position in C, some object in C. Every morphism of it goes to some new object position in P. And so, okay, let me see if I can write this down. So we have, how are we going to get a map from C to poly? What does it do? It takes some object I in C, and it maps it to the sum over all, let me call this something else, J, over all I in P of 1, such that absolute value of I is J. y to the pi. So why does this work? It's saying that if I have this map here, we're going to go over to that part of the board, and we're going to see that if I fix a j in C, an object in C, then all of the positions in P that map to it, along with all of their directions, gives us a polynomial. I mean, that's just automatic. And if I had a map from j to j prime, some f in C bracket j, then I would somehow get a map of polynomials for this to be a functor, not a cofunctor, it's just something easy, not a cofunctor, I prime in P of 1, such that absolute value of I prime is j prime. Okay, let's go figure out why this is true. So we take this object called j in C of 1, and we look at all of the i's that map to it. And all those positions, we take all of their directions. And then the point is, if someone gives us a morphism out from this j to some j prime, like we wrote over there, then we know how to take a position and get a new position. And we know how to take a direction there at the new position and pull it back to one of our old positions. And then you would just check that the conditions on this thing, the epsilon and the delta conditions on this part, would force this to really be a functor. And that's going to say that, that's going to just say these parts here. Identity works and composition works both on the level of objects in P, or elements of P, and on the level of morphisms. Sorry, I should have said on the positions of P and on the directions of P. So that's why it's a functor from C to poly. So if you had a category and you wanted to look at a diagram, like someone said, oh, I have this diagram of polynomials. I have a commutative square of polynomials. Then you would just take a functor from this thing to poly. And if this thing was called C, if someone gave you this, you could think of it like a bicomodule or a comodule. And if you want to take the limit of that thing or other operations you could do on this, you can do that inside of this bicomodule world. Okay, what else? It might be interesting. Okay, and then let's suppose someone gave us a set. How do we get a C set out of it? If they gave us a set X and we had one of these things, well, we could send it to the thing that takes some object in C. J is an object in C, and now we're supposed to get a set for it. Let's just take it to, I don't know what to call this thing, P. P, is that terrible notation? I don't know. P squiggle, P squiggle. Of J, that's a polynomial applied to X. And when you apply a polynomial to X, that preserves connected limits. Polynomials preserve connected limits, and so somehow you can kind of rearrange things and see how you get this part of the thing. Okay, let me do the last thing I was going to say today. What about Y? I might have time to go a little further, but not much. YC by comodules. So if someone looks at, so the following are equivalent. One. A polynomial equipped with this row thing. A YC bimodule. 2. Should I keep talking or? Boop, boop, boop. Okay. Is it working? Shall I continue? Okay. Thanks for bearing with us, everyone. So what is equivalent? A YC bimodule. All this stuff is very abstract, but what I'm trying to tell you with all this abstract stuff is that there's many different ways of looking at the same structures, like linear left and representable right and functors from C to set and all that stuff are all equivalent. So now I'm saying some new one, but it's all pretty abstract. Next time we'll talk about how these are like prof functors, these are like how we actually get to compute like morphisms from database D to database C, etc. And then the time after that, we're going to talk about like a little bit more abstract stuff because one of the great things is that so much works here. But we're also going to talk about data migration and dynamics. But for right now, it's a little bit more abstract stuff, so you can get used to this stuff. So this is P of 1 many, so a set of P of 1 many C sets. So a set of C sets. Now the thing is they're kind of opt. Like a morphism from P to Q will give you a map from P of 1 many C sets to Q of 1 many C sets, but the map of C sets will go the other way. These are not functors from C to set op. Nothing is confusing here. It's functors from C to set, but you just, when you look at the maps between them, they go the other way. 3, well, maybe this is a dumb thing to say, but like, so Josh gave us this adjoint. Then later I found that there was another adjoint to this thing. And so if you take the other adjoint, which I've never even given you notation for yet, but I'll just write it anyway. If you take like P cofunctors from the other adjoint. So what am I talking about? We have this map from P to P composed C. And I can pull this side around in a funny way. And this is the notation for it. And cofunctors from that thing to C are also equivalent. And 4, connected limit preserving. And this is all, number 4 in all these things are the Garner result, prof functors. Parametric right adjoint. Functors from C set to set. Okay, so this takes, and these would be called, maybe I should say another one, disjoint union of conjunctive queries on C. So I'll call these duck queries. Disjoint union of conjunctive queries on C. In other words, if C was a database schema, then these would basically take conjunctive queries, which are like select from where, and then disjoint union of them means you can OR that. Select this from where, or this from where, or this from where. And so duck queries are kind of your most basic, your bread and butter of databases. And so we're getting duck queries from C, duck queries on C. Okay, and why is this? Is there anything worth saying here? I think there is. So it's kind of amazing. I mean, you just run the math and see what it says. And so you have this P, and you have this row thing from P to P composed D. And when you run it, you find that every I in P1, for each I in P1, P bracket I, we kind of said this. We have this Y to the P bracket I thing. And that's a representable right. Y to the P bracket 1, we're getting this thing. So this is like below the line, I guess. We get this representable right D module. And we said that representable right D modules are exactly functors from D to set. So this P bracket I thing, the thing upstairs, is a D set. So each I like when you run this thing through, if you like look over that chart over there, this thing it all stays on the I side. It's just each I in P1 gives you a whole D set. And these D sets they look like this, y to the pi. It's as though y to the pi means it usually means Ham and set from P bracket I to something. When you go back to the very beginning of this course, we said P bracket I is a polynomial, like y to the pi is a polynomial functor. It's representable. You plug in an x and you get functions from this to x. Well, now P bracket I has a structure of a D set. And when we write this thing, we could accidentally, and be okay, we could accidentally think of this as D set maps from P bracket I, the D set, into something else. And those are queries on this something else. These Hams from a certain D set into something are queries on that thing. And so this symbol here, y to the P bracket I, is not just a representable like a functor from set to set. It's a functor from D set to set. Or from, sorry, I guess I said C here. From C set to set. Because it's hamming in this particular C set into any other C set. That's what this symbol could accidentally become taken to mean. And if you think of it that way, it's good. It works. So I guess that's what's happening is we're taking for every I in P of 1. So P is the sum over I in P of 1 of y to the P bracket I. How is this a duck query? It's the sum, disjoint union, of conjunctive queries where you're hamming P bracket I, the representable right. This P bracket I is a C set, and we're hamming that C set in. And so this is a duck query, disjoint union of conjunctive queries. And so I have 3 minutes, so let me just very quickly say what's going on with that. If you have like city, if your database looks like this, city, state, county. Okay, this is a database schema. As a polynomial, it would be y, let's see, 2y squared plus y with a comonoid structure on it. And if you had a functor from this thing to set, it might be a set of cities, a set of counties, and a set of states, and every city was in a state and every county is in a state. So what's a duck query on this? If I took this thing or this thing, I don't know if this is readable or not. If I take a very small little database instance that assigns 1 to each of these, or 2 to this, and 1 to this, and 0 to this, or 0, 1, and 2. There's exactly one way to make a database instance on this thing with 1 thing here, 1 thing here, 1 thing here, or 2 things here, 1 thing here, and 0 things here. There's only one way to do it. And if I do this thing itself becomes, each of these things become a little functor from, if I call this thing D. So we're going to get something like, this thing has 3 elements total, right? You count them, 3. So that would be 3. I hope I don't get this wrong. Darn. 3. I'm probably going to get it wrong. Oh. Yeah, I can't do this. I can't do this on the fly. Sorry about that. Sorry to start. I have 5 seconds left. The point is, you take this thing. We would be able to turn each of these into each of these instances would be a y to the pi. Oh, I can't do it. Y to the 3 plus y to the 3 plus y to the 3, because there's 3 elements in each. And then we would add them together, and we get 3 different duck queries. Even though these are all y3, they act differently in terms of how they're working with the module structure here. We're going to learn about that as we look at our rows. And this thing would migrate this to a set, and it would give you the set of all a city and a county in the same state, 2 cities in the same state or 2 counties in the same state. It would add those all up and give you that answer. Okay, thanks. Oh, thank you, Nelson. Any questions from anyone? All right. Okay, let's stop.